I want to discuss with you about something about the Work-Energy Theorem, which is essentially a tool which can help us in solving many problems. So, for proving this theorem, I have written down the definition of work done. So work done is the integral of f dot dx. So I'll proceed from here, assuming that you know this. So from the Newton's second law, we know that F equals ma. So the work done, then this implies that the work done is the integral of m times a dot dx. Mass is a constant, so I can take it out. This becomes like so. Now we know that a is dv dt, right? So what I can do is I can use a trick. You can call it a trick. Multiply, divide by dx. What this will do is this will create us a term of dx dt, which is v. So v dv dx. So this is acceleration in terms of velocity and distance covered, not in terms of time. So I'll use this definition here. So this becomes m times the integral of v dv dx times dx. So you can see that these dx cancel, and you'll get m times the integral of v, and the integral will go from v1 to v2, and there's of course a dv here. Oops, d by dv. Okay, so what does this become? This will become half m times v2 squared minus v1 squared, or that the work done is equal to half m v2 squared minus half m v2 squared minus half m v1 squared, and this is nothing but the change in kinetic energy. So here we have the Work-Energy Theorem, that the work done by all forces is the change in kinetic energy. So this is not the formal proof of this theorem. There are many more better than this, but I just wanted to give you some basic idea of how this looks. And so let's just do a quick problem based on this. Okay, so here it is. Find the work done which must be performed to increase the velocity of a body from 2 to 6 meters per second over a distance of 10 meters. A constant force of friction equal to 0.2 newtons, this is newtons, acts over the entire distance. The mass of the body is 1 kilogram. So I'll just draw a picture here. This might be the initial state, and this might be the final state. So at the initial state, this is going with a velocity of 2. Here it is going with a velocity of 6, and this distance is 10 meters. And this is 1 kilogram. Okay, so and there is a friction which acts in the backward direction, like so, which is of the magnitude 0.2 newton. Okay, so I'll just use what we derived just now. Work done by all forces is change in kinetic energy. So what all forces are acting here? There is a work done by a friction, and there is a work done by me, which is equal to the change in kinetic energy. So work done by friction will be, let me write it here. Work done by friction will be the force of friction times the distance, and that will be equal to 0.2 times the distance, which is 10, and so this is -2. And you'll be surprised that there is a negative, because and that is because the force is in opposite direction and displacement is in the right direction. So the work done by friction is negative. That's usually the case, but sometimes it isn't. In this case it is negative, so it is negative 2 Newton. I'll keep my work done like that. So okay, so what is the change in kinetic energy? It is 1/2 times 1 times v final square minus v initial square, so that is 6 squared minus 2 squared, so I get negative 2 plus w me is equal to 36 minus 4 is 32, divided by 2 is 16, so work done by me will be equal to 18 newtons. So that is the answer here. We have to do a work of 18 newtons to increase the distance velocity of a body of 1 kilogram mass from 2 to 6 over a distance of 10 meters. So yeah, I hope you like it, and we'll use this definition in some problems.